In this video, we're going to do some problems where we're going to find the Taylor series, or Taylor polynomial, actually, of some functions here. So we're going to start, well, really one function. Start with our function. F of x, we're going to work with is x divided by 3 minus x squared. Here. And we're going to do two things here. One, or A here, is find the Taylor polynomial for f of x of order, so this is really how big of a power of x we want in the polynomial. Let's just do order 3 here, except that's not enough. We're going to do this centered at 0. So this would be a Maclaurin series, or really your Maclaurin polynomial, because we're centered at 0. And then when we're done with that, we're going to do the same thing, but centered at 2. So I'm just going to copy this. Paste. There we go. So essentially the same thing. So I don't want this to be sort of A. This is part B. And centering at 0, now we want to center at 2. So these are really the two questions I'm going to work on. First of all, Taylor polynomial for f of x of order 3 centered at 0, and then centered at 2. Here. And I'm going to do both of these in two ways. So first of all, I'm going to do a straightforward method, sort of just using the definition of a Taylor series, or I guess Taylor polynomial. And then I'm going to go and derive the Taylor polynomial from some known, really the Taylor series, from some known series. So let's do A here. Part A. And this is, again, f of x is 3, not 3, x over 3 minus x squared. And we're looking at this centered at 0. Here. So this we can do in a very straightforward way. Our Taylor series here, so our Taylor series essentially is going to tell us that x over 3 minus x quantity squared will be a sum n equals 0 to infinity. And I take the nth derivative of f, evaluate that at 0, divide by n factorial, and then I get an x to the n. So as long as the series on the right converges here, this equality will be true. So this is essentially, what we're going to try and do, and we've got everything we need here, except for the nth derivative of f. Here. So you could try and do a formula for the nth derivative of f, but if we do the Taylor polynomial, of order 3, essentially what we get is x over 3 minus x squared. We're going to now approximate this. It's not really equal. We're going to do n equals 0, and instead of going up to infinity, we're going to stop at 3. X to the n, and what that sort of series equals is when n is 0, we get really f of 0 plus f prime evaluated at 0 of x. If you plug in n equals 1, you get 1 factorial is 1. And then we'll get plus f second derivative evaluated at 0 divided by 2 factorial is 2 times x squared. And then plus f, you take the third derivative, or f triple prime, evaluated at 0, divided by 3 factorial, which is 6, times x cubed. So this is really our Taylor polynomial of order 3. Here. So if all you want is the Taylor polynomial of order 3, you can take derivatives of f. You only need to get to the third derivative and just evaluate those at 0. Here. And that will work out, sort of just fine. If we wanted the actual Taylor series, we wanted to go up to infinity, then we'd have to take enough derivatives so we can see a pattern. I guess technically you'd want to prove that by induction, that your pattern is correct for this nth derivative of f evaluated at 0. It gets a little more complicated here. But the small number of these derivatives, it's not so bad. So now we're going to find the derivatives. And this is the part we can avoid with the method later on. So f of x was, again, x over 3 minus x quantity squared. So f of 0 here is going to be 0 over 3 squared. That's 0 over 9. That's 0. So really our constant term, this f of 0, is just 0. Drops out. F prime of x, we have to use quotient rule. So that's bottom 3 minus x squared times the derivative of the top is 1 minus the top is x times the derivative of the bottom is 2 times 3 minus x times the derivative of the inside of that 3 minus x squared is really a negative 1. So bottom times derivative of top minus top times derivative of the bottom over the bottom squared. So 3 minus x squared, when I square that, that's going to double the exponent to 4. So you get this expression here. You could evaluate 0 here now, but I'm going to try and simplify this a little bit just for taking the second and third derivative's sake here. So what I can notice is on top, I have a 3 minus x as a factor in sort of both my terms here. So I can pull out a 3 minus x. On the sort of left term or first term, what I'm left with is another 3 minus x. On the right, this second term, I have an x times 2 times a negative 1. The negative 1 will cancel the minus. So that's plus 2x over 3 minus x to the fourth. And then I can cancel a 3 minus x factor on top with a 3 minus x on the bottom. And that gives me, let's see, 3. Negative x plus 2x is plus x over, I'll end up with a 3 minus x cubed. So I found my first derivative. I did some work to simplify that, so taking the next derivatives is a bit easier. And what I need for my Taylor polynomial is to evaluate this derivative at 0. And so that's going to be 3 on top divided by 3 cubed on the bottom. Let's see, so I can cancel a 3 top and bottom. That's 1 over 3 squared. That's a 9th. So 1/9 there. So we're sort of building up our Taylor polynomial. We're going to need a second derivative now of x, and then we'll get that and then plug in a 0. So our second derivative, we're going to take 3 plus x over 3 minus x cubed, take its derivative. You get the bottom, 3 minus x cubed, times the derivative of the top, just 1, minus the top, 3 plus x, times the derivative of the bottom. I get a 3 times 3 minus x squared times the derivative of the inside is a negative 1. Just using the chain rule there. And then quotient rule says I square the bottom. That's going to double the exponent, so it'll be 3 minus x to the 6th. And then we can do the same thing we did with the first derivative. I can factor out some of my 3 minus x's. Note I have a 3 minus x cubed and then a 3 minus x squared. So I can factor out actually a 3 minus x squared. On the left, what I have remaining is 3 minus x. On the right, I have a minus 1 times a negative, that's plus. So I'll get a 3 times 3 plus x. And what that's going to be is 3 times 3 is 9. 3 times x is plus 3x. On the bottom, I have 3 minus x to the 6th. And so what I get, let's see, 3 minus x squared, I can cancel some of these out, get a 3 minus x to the 4th. And let's see, 3 plus 9 is 12. 3x minus x is plus 2x. So that's my second derivative of f. For my Taylor polynomial, I need to evaluate that at 0. So when I do that at 0, I get 12 over, so I put in a 3 to the 4th. And what I'm going to get, let's see, 12 is 3 times 4 over 3 to the 4th. So that's going to be 4 over 3 cubed. That's 4/27. So I get my Taylor polynomial of 4/27. All right. Now we got to do our third derivative here. So let's see what we get. Let's see. So the third derivative, triple prime of x. See, I've got 12 plus 2x over 3 minus x to the 4th. Take its derivative. I get 3 minus x to the 4th, bottom, times the derivative of the top, which is 2x, minus the top, 12 plus 2x, times the derivative of the bottom is 4 times 3 minus x cubed, times the derivative of the inside of that is a negative 1. Then I divide by 3 minus x, double the 4 to an 8, squaring the bottom. And then here, same thing as before. I can factor out a 3 minus x, this time to the 3rd. I'm left with a 3 minus x times 2. Minus 1 times the negative gives me a positive, plus the 4 times the 12 plus 2x. So that's 48 plus 8x. And then I'm going to divide by 3 minus x to the 8th. And so let's see what I get. I can cancel a 3 minus x cubed. So I'll end up with a 3 minus x to the 5th here. And then let's see, 2 times 3 is 6, plus 48 is 54. 2 times negative x is negative 2x, plus 8x is plus 6x. So there's my third derivative. So if I evaluate that at 0, I will get 54 over 3 to the 5th. Note 54 is 27 times 2. 27 is 3 cubed. So this is 2 over 3 squared. This is really just 2/9. So we got a first derivative, second derivative, third derivative, and I guess the function evaluated at 0. So now our Taylor polynomial of order 3 centered at 0. So it's a Maclaurin polynomial. What we get, okay, so let's go back up here. Let's just copy what we had for our Taylor polynomial. Let's copy this over. You get that. Copy that. Move it down here. Let's paste that. Okay. So this is our Taylor polynomial. Now we're going to just fill in our values. So f of 0. So we did that up here. F of 0 is 0. So f of 0 is 0. So we put a 0 plus f prime of 0. First derivative value at 0 was 1/9. So you get a 1/9 times x plus second derivative valued at 0 was 4/27. But then you have a divide by 2, x squared. Third derivative evaluated at 0 is 2/9 divided by 6, x cubed. And then if you want to simplify this, let's see, 0 goes away. I get x over 9. 4 divided by 2 gives me plus 2/27 x squared. Plus, let's see, 2 and 6, I can cancel a 2. This is going to be a 1/27 x cubed. So this is really my Taylor polynomial of order 3. All right, that works out just fine. It's straightforward. To me, this is a little bit annoying because I have to go and take these derivatives. I'm actually a little bit worried I may have made a little mistake during those calculations here. So we want to do a little bit better method here, a little different method. So we do a different method. So again, what I'm looking for is 3, not 3. I just want to put a 3 there. It's x over 3 minus x squared. This is the function I'm trying to find my Taylor polynomial for. And what I'm going to notice is I have this sort of 1 minus, or constant minus something in the bottom. So what I'm going to think about is, oh, hey, I know a series, 1 over 1 minus x. I know that that's n equals 0 to infinity x to the n. So this is one of our sort of building block Taylor series here. 1 over 1 minus x centered at 0 gives me a sum n equals 0 to infinity. It just turns out to be x to the n here. You could take the nth derivatives here. It's not that bad. You get the nth derivatives n factorial, and that cancels the factorials in the Taylor series sort of definition here. So you could get this here. Now, what I want to do, though, is I want to get a square on the bottom here. So I want to get that square on the bottom, and this takes a little bit getting used to, but I'm going to differentiate 1 over 1 minus x here. And see, so that's the derivative 1 minus x to the negative first. So that derivative is going to be a negative 1 times 1 minus x to the negative 2. And then I differentiate by the inside of the 1 minus x here. That's a negative 1. So I get it essentially a negative 1 and a negative cancel. And I end up with 1 over 1 minus x, quantity squared. Okay, so now we're getting pretty close to what we have here, x over 3 minus x squared. At least we're getting closer. Couple issues. We have that x on top, and we have a 3 instead of a 1. Okay, so it turns out now, we have the 1 over 1 minus x squared. That was our derivative. I guess that's not any good, really, without this series here. So what we can do is say that 1 over 1 minus x quantity squared should be a derivative with respect to x of a sum n equals 0 to infinity x to the n. and that's going to be a sum n equals 0 to infinity, derivative with respect to x, x to the n. We can interchange our derivative and our summation as long as we have our enough convergence, which we will here. And then we get a sum n equals 0 to infinity. Derivative of x to the n is n times x to the n minus 1. Now, I'm going to want to rewrite this so my exponent is n. Before I do that, I'm going to note that if I plug in n equals 0, I get a 0 here. So the first transformation I'm going to make is this summation. I can just start at 1 instead of 0. And the reason I can do that again is that if you plug in an n equals 0, the term is 0 already. So if you don't add that term, you're not adding 0. It doesn't affect anything. Then what I'm going to do is I want this n minus 1. I want to replace n with n plus 1 in the sort of summands. I get n plus 1 times x to the n. So I sort of add 1 to n everywhere I see it inside. And the corresponding action to take is that means I have to decrease 1 from n on the outside. So it's kind of like a substitution in an integral here. So it ends up here that what I get is 1 over 1 minus x squared is summation n equals 0 to infinity, n plus 1 times x to the n. I should say, if you don't understand this step where I went from the n equals 1 to infinity back to the 0 to infinity, just write out the first few terms. So this one over here, just do this. This series, if you write out n equals 1, that's 1 times x to the 0, plus n equals 2 is 2 times x to the 2 minus 1 is 1. N equals 3 is 3 times x squared here. And then this series, if you do n equals 0, you get 1 times x to the 0, which is 1, plus n equals 1 gives you 2 times x to the 1. N equals 2 gives you 2 plus 1 is 3 times x squared, plus blah, blah, blah. Note we're getting the exact same thing for both of these two series here. So that's really some manipulation. Takes a little bit to get used to. Okay, so let's recap what we have here. So we have a sum n equals 0 to infinity, n plus 1 x to the n. That is 1 over 1 minus x squared. So we sort of derived that series by taking a derivative from a known series. And then what we're looking at is we want to get a series for x over 3 minus x squared. So the idea is this x over 3 minus x squared looks kind of like 1 over 1 minus x squared. To deal with the x, I'm just going to kind of factor that out. So what I'm going to get is a series for 1 over 3 minus x squared here. And I can multiply by x. We can deal with that later on. So x is a pretty nice thing to multiply by for a power series. But then this 3 minus x squared, I need to make that a 1 here. So what I'm going to do is just factor that 3 out on the inside. So what I'm going to do, let's do a square bracket. This is 3 times 1 minus, well, I have to factor 3 out of x. That gives me an x over 3. So if you did 3 times 1 gives you 3. 3 times x over 3, that gives you the x. So this is just the same thing. I wrote 3 minus x in kind of a funny way, but I wanted to get a 1 here, and that's really our goal here, is to get that 1 minus. And so this is x times 1 over, and now I can pull the 3 out of the square. That's going to come out as a 3 squared, which is 9. 1 minus x over 3 squared. So altogether, this is x, and then you can pull the 9 over, x over 9, times 1 over 1 minus x over 3 squared. Now we have a 1 over 1 minus something squared. Note our x isn't the same, but you could just put x over 3 where you see x in your series. So now what I can do is x over 9 times the summation n equals 0 to infinity. Get an n plus 1, and then it would have been x to the n, but I'm not plugging in x. I'm plugging in x over 3. Okay, from here, I could get my Taylor polynomial of degree 3. You could just plug in n equals 0, n equals 1, n equals 2. You only have to go up to 2 here because you have an extra x on the outside here. And that would get you your Taylor polynomial of degree 3. I'm going to talk about how to rewrite this whole thing with the multiply by x over 9 as a new series just to get some practice with that. So what I'm going to do is I'm going to bring the x over 9 inside here. Actually, before I do that, I'm going to take the x over 3 to the n divided by 3. So let's actually do both of those. So we have n equals 0 to infinity. I can bring in the x over 9. I have an n plus 1. And then x over 3 to the n is x to the n divided by 3 to the n. Okay, now what I'm going to get is n equals 0 to infinity. X, let me write the n plus 1 here. X times x to the n is x to the n plus 1. 9, note what I'm going to think about here is this 9. That's really a 3 squared here. So 3 squared times 3 to the n is 3 to the n plus 2 on the bottom. Now, I'd like this to be an x to the n instead of an x to the n plus 1. Here, so I'm going to pull my trick where I'm going to replace n plus 1 with n. Here, so I'm going to get an n times x to the n. 3 to the, let's see, it'll be n plus 1. I sort of subtract 1 everywhere I see an n. But I'm sort of going down 1 from the n's on sort of the sum n's. Means I have to go up n equals 1 to infinity sort of in the index here. And in some sense, this is my power series. So this is x over 3 minus x squared. So it's my power series or Taylor series here. And these two should be the same wherever the series on the left actually converges here. All right, so now our Taylor polynomial, all you do is you plug in n equals 0, n equals 1, n equals 2, n equals 3. So what we're going to get here, there's no n equals 0. That term went away. So we're going to plug in n equals 1. So we'll get 1 times x to the n over 3 squared. That's 1/9 x. Plus, when n is 2, we get 2 over 3 to the third. That's 27 x squared. And then when n is 3, we get 3 over 3 to the fourth times x to the fourth. So this is our Taylor polynomial of order 3. Oh, sorry. It would be, except n was 3, so x third. I noticed it was x to the fourth. Should not be in a Taylor polynomial of order 3. Just made a mistake, probably because I saw the 3 plus 1 is 4 there. Copy that over, but it should be a 3. X to the third. And so this is 1/9 x plus 2/27 x squared. And then 3 over 3 to the fourth is 1 over 3 cubed. So that's 1 over, let's see, 3 cubed. That's, whoops, sorry, 3 cubed is not 81. 3 cubed is 27 x cubed. So we can get our Taylor polynomial instead of by taking derivatives and evaluating it at a particular point here. You can get essentially a Taylor polynomial by finding a Taylor series and then taking the first so many terms of that. Just check that the answer is the same. So 1/9, 2/27, 1/27. Before we got 1/9, 2/27, 1/27. So we got the same answer both ways, which is good. Here, just sort of check for mistakes. Okay, now here I realize probably doing this using the series is a little bit complicated. Couple issues here that caused that. One is we had to do some work to get a series for 1 over 1 minus x squared. If your original function here had a known power series already, or known Taylor series, you can avoid that step. So this whole business up here, you might have been able to avoid here. Another thing where we sort of did more work than is, well, maybe work is not as efficient as it seems, is with this second method, if I want to find a Taylor polynomial of degree 4, or sorry, order 4, I just go and pull off another term. So I'd get 4 over 3 to the 5th. 3 to the 5th is 243. So I get 4 243rds of x to the 5th, or x to the 4th, I mean. So you could keep adding more and more stuff here pretty easily now. Whereas the derivative method, I've got to keep taking more and more derivatives. That's going to start to get a little bit annoying eventually. Maybe you do that enough and start to come up with a formula for the derivatives. Any case, a couple methods here. That was A. So part B, we wanted to do a Taylor polynomial for x over 3 minus x squared. Same function. And we want a Taylor polynomial of order 3, but now we're going to do this centered at 2. So centered at 2 instead of centered at 0. So what that's going to look like here, our Taylor series, is this is going to be a sum n equals 0 to infinity. And now it's going to be the nth derivative, but now we evaluate at 2, still divide by n factorial, and then instead of x to the n, you get an x minus your center, which is x minus 2 to the n. And so in the end, what you're going to get, here's if you plug in n equals 0, you're going to get a f of 2 divided by 0 factorial is 1, x minus 2 to the 0 is 1, so just f of 2, plus f prime of 2 divided by 2 factorial, sorry, not 2 factorial, 1 factorial is 1, so that's really no division, and then times x minus 2 plus f double prime evaluated at 2. This one will be divided by 2 factorial, which is 2, times x minus 2 squared plus f triple prime evaluated at 2 over 3 factorial is 6 times x minus 2 cubed. So essentially you can get this Taylor polynomial of degree 3 or order 3 by just sort of taking the previous series, but you take derivatives evaluated at different points and you replace x with x minus 2. Now, given that we did part A, one of the nice things is we already have formulas for our derivatives here. So let's go through and find these here. So f of 2, we have to plug in different points, so it's not the same value. So 2 instead of 0. So this is 2 over 3 minus 2 squared. That's 2 over 1 squared. That's 2 over 1. That's just 2. So that's f of 2. Well, then f prime of 2, let's go find f prime of x. Way up here. So f prime of x is 3 plus x over 3 minus x cubed. So that was 3 plus x, which is 2, over 3 minus x is 2 cubed. So this is 5 over 1 cubed. That's just 5. F second derivative evaluated at 2. Let's go find our formula for the second derivative. Here, we had to go up here. Let's see. It was 12 plus 2x over 3 minus x to the 4th. Here, 12 plus 2x. So it's 12 plus 2 times 2 over 3 minus x to the 4th. Except it's, well, it's 3 minus x, but we're plugging in a 2, so 3 minus 2 to the 4th. So that's 12 plus 4, that's 16. Over 3 minus 2 is 1 to the 4th, that's 1 to the 4th is 1. So that gives us a 16. And then the third derivative evaluated at 2 is 54 plus 6x over 3 minus x to the 5th. So I get 54 plus 6 times 2 over 3 minus 2 to the 5th. So you get 54 plus 12, that's 66, over 1 to the 5th. That's just 66 here. All right, so what that means, you can sort of put this all together, is that our Taylor polynomial of order 3 is f of 2, that's 2, plus f prime of 2, that's 5, times x minus 2, plus, and then the next one is f double prime of 2, that's 16, but we divide by 2 factorial is 2, times x minus 2 squared, plus f triple prime of 2, that's 66, divided by 3 factorial is 6, times x minus 2 cubed. And so what we get really is 2 plus 5 times x minus 2 plus 8 times x minus 2 squared, plus 66 divided by 6 is 11 times x minus 2 cubed. So this is really our answer here. Now, warning here is there's a temptation here, and I'm fighting this a little bit myself, is to take 5 times x minus 2, turn that into 5x minus 10. And to like square out x minus 2 here, you get x minus 2 squared, and then you multiply that by 8. There. So that should work out sort of just fine here. I mean, in some sense it should work, but we don't want to do that. Generally, when we have a Taylor series or Taylor polynomial centered at 2, we're trying to approximate some function near 2, which means x minus 2 is actually an easier form to work with than having an x. Here. Now, Yeah, and so essentially, I mean, we're just going to leave those x minus 2's there. All right, so that's the first method. Now let's use the second method here. And that second method, we take 3. Sorry, not 3. I don't know why I want to put a 3 there. Take x minus 3 minus x squared, and I want to rewrite this using sort of known Taylor series here. So I'm going to use the same idea before, is that 1 over 1 minus x was sum n equals 0 to infinity x to the n. And if you differentiate both sides, you get 1 minus 1 over x squared. This gave us a sum n equals 0 to infinity n plus 1 x to the n. So this series I'm going to use from before here. It's really the same series we used before. Here, so you can go through and derive that again if you want. Now, but this is centered at 0. It's not centered at 2. So what I want to do is I want to replace my x. I have my n plus 1. I'm going to replace my x with an x minus 2 to the n in the series, and that would be centered at 2. Well, that means on the left, I have to replace x with x minus 2 as well. And so this is 1 over 1 minus x plus 2 squared. Note that's 1 over 3 minus x squared. Well, that's convenient. That's exactly the denominator we have before here, so, or exactly the denominator we want. That's going to help us out here. So we get 1 over 3 minus x squared equals sum n equals 0 to infinity n plus 1 times x minus 2 to the n. So now we can use that. And what we have is almost exactly this, but we have an x on top. So we have x over 3 minus x squared here. And I want to write this as 1 over 3 minus x. So I can do this x times 1 over 3 minus x squared. And that tells me this is x times the sum n equals 0 to infinity n plus 1 times x minus 2 to the n. Now, before we just took the x, moved it in, and essentially increased the exponent by 1. But that would be if we have an x to the n. We have an x minus 2 to the n. So what we need to do is rewrite x sort of in terms of x minus 2. This is going to feel weird, but what that's going to look like is x minus 2 plus 2. So that's x there, just written with an x minus 2, times the sum n equals 0 to infinity n plus 1 times x minus 2 to the n. And then I'm going to get two separate series. I'm going to get an x minus 2 times the sum n equals 0 to infinity times n plus 1 x minus 2 to the n plus the 2 times the sum n equals 0 to infinity n plus 1 times x minus 2 to the n. So now the goal is to sort of simplify both these series and then add them back together to get one series. So this left one, I can move the x minus 2 in the inside. I get n equals 0 to infinity n plus 1. When I move that x minus 2 to the inside, I just have one more factor of x minus 2 that's going to increase the exponent from n to n plus 1. On the right, the 2 is going to come inside. I'm just going to get a 2 times n plus 1 x minus 2 to the n. Okay, and now I'd like to add these together, but I have x minus 2 to the n plus 1 versus x minus 2 to the n. I want those both to be x minus 2 to the n. So in this left one, what I'm going to do is I'm going to replace n plus 1 with n. That's sort of replacing every n with an n minus 1. And that means my index has got to go, say, went down 1 inside. I'm going to go up 1 on my index. N equals 1 to infinity. Plus, on the second one, I'm just going to distribute that 2. So that's 2n plus 2. X minus 2 to the n. Now, these two I'd like to combine, but I have a problem. I have an starting n equals 1 on the left and starting at n equals 0 on the right. So what I can do is I can pull off the n equals 0 term on the right, and then it would start at n equals 1. So what I'm going to get now is a sum n equals 1 to infinity n times x minus 2 to the n. So that's really this series. And then my other series is when I plug in n equals 0, I'll get 2 times 0 is 0. I get a 2. X minus 2 to the n is just 1, so I get a 2 plus sum n equals 1 to infinity. 2n plus 2, x minus 2 to the n. I could have done a 2 plus whatever I get inside when I plug in n equals 1 and done n equals 2 to infinity. Here, that would work, but I want to match the n equals 1 to infinity with these series. Okay, so now what I'm going to do is, let's say I have the 2, I'm going to put that out in front, plus sum n equals 1 to infinity. On this left, I have n times x minus 2 to the n. On the second sum, I have plus 2n plus 2 times x minus 2 to the n. So this works out to be 2 plus sum n equals 1 to infinity. So I can factor out an x minus 2 to the n from both of the terms in here. So I get an n plus 2n plus 2 times x minus 2 to the n. So that gives me a 2 plus sum n equals 1 to infinity. N plus 2n plus 2, that's going to be a 3n plus 2 times x minus 2 to the n. Now, note, I would generally stop here, but if you do an n equals 0 on the stuff inside of here, you actually get a 2 times 1. You actually get the 2. So you could rewrite this as n equals 0 to infinity, 3n plus 2, x minus 2 to the n. So that actually works as well. Probably the reason why here is, let's see, when I have this series n equals 1 to infinity, I could have changed this 1. So note that this series here, sum n equals 1 to infinity, n times x minus 2 to the n, that's actually the same thing as n equals 0 to infinity, n times x minus 2 to the n. So you just decrease where I start from 1 to 0. The reason I can do that is that if you plug in n equals 0, you get 0 times something, you just get 0. So adding in another 0 doesn't change the sum. So you could have done that, and then I would have just matched here. And that probably would have actually been easier to do. In any case, we get down to this series, and this was for x over 3 minus x squared. And so our Taylor polynomial of order 3, centered at 2, all you do is you plug in n equals 0. That gives you a 2. Plus plug in n equals 1. 3 plus 2, that's 5. And then it's x minus 2. Then plug in n equals 2, you get, let's see, 6 plus 2 is 8. Note 5 plus 3 more gives us 8 because it's a 3n. And it's x minus 2 squared. And then the next one will be 11 times x minus 2 cubed. Next one will be 14 times x minus 2 to the fourth, but we don't need that one. So our coefficients are 2, 5, 8, and 11. Let's go back up. 2, 5, 8, 11. Everything works out just fine. So there we did this series this Taylor polynomial. We found it in two ways. One was sort of directly. The other is using these series manipulations. I'm a little worried these examples aren't showing you sort of the power of the series manipulations here, where it seems like taking the derivatives might have been simpler. But note, these series manipulations, again, I can keep going and find the degree 4, degree 5, degree 6, degree 7 Taylor polynomials. Whereas with the derivative approach, I'd have to keep taking derivatives, which is going to get old at some point. There's other things where once in a while those derivatives just get really ugly and big here. In our case, that didn't really happen, though.